The next series we want to look at is called a geometric series. If you've studied anything to do with series in the past, you would have seen this geometric series. So we want to first let a and r be real numbers, a not equal to 0. The geometric series is basically multiplying each term by a constant multiplier. So you start with a, and then you multiply by r. So the next term is ar plus ar squared plus etc. So the nth term is one less than the first term. So a r to the n minus 1 is the nth term. So that's a geometric series. In summation form, it would look like the sum of a r to the n minus 1 as n goes from 1 and then approach infinity. So that's the geometric series. Converges if the absolute value of r is less than 1. And we say it actually converges to, we can calculate this, to a over 1 minus r is what the sum converges to. So you can actually say this equals s. And then diverges otherwise. So it diverges the absolute value of r is greater than or equal to 1. So we'll show when it converges. So to do that, first let's look at a partial sum. So we can argue if r is 1 or greater than 1. Little details will be in the book, but let's just look at this case. So just kind of an illustration. So let's look at S sub n. S sub n is a plus ar plus ar squared plus etc. all the way to ar to the n minus 1. So now think of it like this. So we know that's the nth partial sum or kth partial sum of the geometric series. So now multiply both sides by r. So multiply on both sides by r. So what you would get then is r Sn ar plus ar squared plus ar cubed, etc., plus ar to the n. So now subtract both equations, just like you would like two equations, like you're solving two equations, you gotta like eliminate. So subtract two equations, or the two equations, and you'll get Sn minus Rsn equal to, and then we can see that you're going to get these terms to be annihilated basically, all the way down to the last term. So what you end up getting is a minus ar to the n. And then essentially you solve that for S sub n. So if you solve for S sub n, you'd factor out S sub n. And that's 1 minus r equal to a times 1 minus r to the n all over 1 minus r. So now then divide, and you get s sub n is equal to a times 1 minus r to the n over 1 minus r. So that's the sum of the first n terms of a geometric sequence. Often they put that in parentheses. We could break this up a bit if you wanted to and write this as a over 1 minus r minus ar to the n over 1 minus r. So then from there, if you look at the limit as n approaches infinity, so now look at the limit as n approaches infinity of s sub n, we can see that this is going to 0 because r to the n is approaching 0. If, so that's true only if absolute value of r is less than 1. So you're raising a fraction between 0 and 1 to infinity, it approaches 0. So that limit then is a over 1 minus r. Okay, so that's the concept of why that converges. So those other details, but basically if that fraction is, or the r is between 0 and 1, actually if it's between negative 1 and positive 1, then the geometric series converges. Okay. Now let's look at another theorem. This is called it leads to what's called the nth term test. So we'll just call this a theorem. Basically says if a series sum of a sub n converges, then the limit of a sub n as n approaches infinity must equal 0. So if the series converges, then it has to be true that the limit of the nth term of the series approaches 0. Now, and I'll leave the proof off for now. I'll maybe come back to that if I want, but actually we need to apply this. What I want to do next actually is a little bit of a logic discussion. Logic. All right, so for logic, so to understand how to do some of these proofs, you got to get some of these logic concepts down. So if you have P implies Q, so that's red, P implies Q. So if you have that statement, then it's an implication one direction. So if it's raining out, so here's an example of one. If it's raining outside, then the grass is wet. So is going the other direction true? So if the grass is wet, or will get wet or whatever, did it rain? Is it raining? And we know that that's not true because it could have been sprinklers on or something like that. Right? So it goes one direction. So the converse is Q implies P, and that is not logically equivalent. And you could use kind of any sort of implication you want to can come up with. So it's not what we say is logically equivalent. However, okay, so that's the converse. The converse is not logically equivalent. However, if you say, so we use this symbol for logically equivalent. So what is logically equivalent is what's called the contrapositive. So not Q implies not P. And that's read not Q, or the negation of Q implies the negation of P or not P. I'll put the not in there. So it's not or negation. All right. So what this can be used for is, so an example of this, just to be clear, this is a true theorem, but we only use this theorem really to show divergence. It's really used mostly, almost entirely for this contrapositive. So if the limit of the nth term does not approach zero, then the series does not converge. So if you reverse that, that's what's called the nth term test. Okay, so let's look at that. This is the nth term test. So the nth term test is used to show divergence. Put that down. Used to show divergence. So what it says then is this. So if the limit of a sub n as n approaches infinity does not equal zero, this is the contrapositive, then the series a sub n diverges. Okay, so if the limit of a sub n equals zero, then let's just say further tests are needed. Further tests, examinations, whatever. You got to figure it out. Further tests are needed. And that's frankly what the rest of this chapter is about. Well, most of the rest of the chapter is about is all these different tests to show convergence and divergence. So the nth term test only shows divergence. Right? Maybe I should have said only. So only shows divergence. So let's look at a few examples. All right, so this is just like a table of examples. So we're going to look at the series, look at the nth term, and conclusion. So the conclusion is either going to basically say diverges or further investigation. That's all I really have. So we'll look at we'll look at a few of these cases. So these all approach infinity. It's always 1 to infinity. So we'll kind of speed up some of the notation a little bit. All right, so the sum n over 2n plus 1. The sum 1 over n squared. The sum 1 over root n. And the sum e to the n over n. So the nth term test, what do you do to show or kind of go from there? What you do is you have to see what happens to this limit, the limit of a sub n. If it's not 0, like you get 3 or something, then you're done. The series diverges. I mean, it's automatic. Okay, all of those are approaching infinity. I just want to make that clear. So you check out the limit. You look at the limit of n over 2n plus 1 and see what happens. And we know that that is 1/2, which is not equal to 0. Conclusion, diverges. And you want to say by the nth term test. So let me move that over. So you want to make sure you say, I'll be looking for that, in other words. Diverges how? By what test? By what rationale? You have to be able to say all that. So this one, the limit 1 over n squared. That does equal to 0, so that's case 2. No conclusion. Further tests are needed. Limit 1 over root n, what does that equal? Yes, equals 0 as well. Again, no conclusion. And then this one, this one might, well, how could you prove this one? Yeah, you could do, so if you look at this one, e to the n over n, one way to interpret it is knowing that e to the n grows much faster than n. So this is going to take off to infinity. So it's like saying this really diverges. Well, it doesn't really matter, but so this is actually approaching infinity. It's not even approaching a finite number. But you can actually show that by L'Hopital's rule, right? You have e to the x over x. If the real valued function approaches something, then so does the sequence. We showed that we saw that in the last section. So this actually equals infinity. So diverges by the nth term test. Okay. Well, I think that's it. There's a few other things in that section you may want to take a look at. Oh, there's some properties and stuff. So, yeah, let's look at this property here. So we have another theorem. Those will be the last theorem. I'm not going to spend time like talking about it, but it should make sense. It should be pretty clear when you see it. So if the sum a sub n and the sum b sub n converges, and I won't run all the little details. Basically, it's saying then that the sum a sub n plus b sub n converges. Some of the books that I used to use, like the advanced books, they would say like this, less than infinity, just to speed up the notation. And then so that basically implies it converges. Sometimes I might slip up and do that. So in any case, that sum would converge, and it actually converges to whatever these converge to. And then if you put in an arbitrary constant, Cn, that also converges. If you do a difference, that also converges. Okay, and it converges to what you would think it converges to. You just take the difference of whatever it is. So if this was capital A and this was capital B, then the sum converges to A plus B. This converges to C times A, and this converges to A minus B. So just some properties of summations. So you'll look at some geometric series and some of the other content we saw in here on that section. And the next we get into